Let us now talk about the expressiveness of MPNN. Specifically, we're going to discuss simple MPNNs, and we're going to discuss expressiveness from a specific viewpoint, basically the ability of MPNNs to separate between graphs or between nodes. Okay, let's see how it goes. We are going to use the Weisfeld-Lehmann isomorphism test. And basically what we're going to say is that the expressive power of simple MPNNs is the same as that of 1WL, again, as far as separation is concerned. Okay, let's recall first the Weisfeld-Lehmann test of isomorphism. We color basically the nodes in iterations. Here we apply k iterations of the coloring. We start by assigning the color 0 to every node, u, and then in each step, we say that the ith color of u is a hash of the previous, the I minus first color of u, comma, the bag of colors of the neighbors of u from the previous iteration. Okay, that's a 1WL. Okay, and then we extended it to featured graphs. And basically it was the same, except that this initial color is not 0, but rather a hash over the features of u. Okay, hash of x u. Now, for things to be well defined, in particular for this hash prime function to be a perfect hash function, injective, we need to assume that the features come from some countable space. Okay, from some discrete space, for example, the integers. Okay, now, with that, here are the theorems. So suppose that gamma is a simple MPNN. Consider two nodes, V and V prime of G. Now, if 1WL assigns to V and V prime the same color after L steps, then when you apply gamma, at least L layers, or exactly L layers of gamma, or at most L layers of gamma, then they will have the same value in the MPNN gamma. Okay? In notation, if kappa L of V equals kappa L of V prime, then the value after the Lth layer, HV of L, is the same as HV prime of L. Okay? So in other words, L layers of MPNNs cannot distinguish what 1WL cannot distinguish after L steps. Okay? Now, if you think of applying WL to the graphs themselves, so we have G1 and G2, and suppose that they are isomorphic according to WL. Okay, they're not necessarily isomorphic, but suppose that WL thinks that they are isomorphic. Okay? Then the MPNN will also construct the same matrix of values, of representations, HL. For them, of course, up to a permutation. Okay, because isomorphism allows for reordering of nodes. Okay, so that's one thing. On the other hand, we can simulate WN with MPNNs. MPNNs are not fundamentally less expressive than WL. Specifically, what the theorem of Morris et al. Says is that there is a simple MPNN, okay, or for every graph G, we can find a simple MPNN. And this MPNN actually is very simple. Basically, your aggregation, well, message function is, of course, copying the previous layer of the neighbors. And the aggregation is a summation, and the update is just a linear update. And on top of that, you apply ReLU. Okay? So it's ReLU over a linear combination where the aggregation function is sum. So we can construct such an MPNN such that we have the following for every layer L. Take any two nodes, V and V prime. WL, or one WL, assigns to them the same color after L steps, if and only if gamma assigns to them the same value over L layers. Okay, of course, we assume here that when you encode the graph as a feature of the graph, all of the nodes have the same value. Okay, that's why we can apply the MPNN to the graph, even though it doesn't have features to begin with. Okay, so in notation, we have, again, kappa L of V equals kappa L of V prime, if and only if the Lth representation of V is equal to the Lth representation of V prime. So you can see that we can construct uh, an MPNN that basically simulates WL. Okay, and these are basically examples of failures in the sense that these are pairs. Every column is a pair of non-isomorphic graphs, where WL gives the graph and different nodes the same color in terms of the lineup of colors. W thinks that they are isomorphic. Okay, so you can see here that the same applies to every MPNN or simple MPNN. Okay, and we've seen other examples in the previous lectures.